evening and welcome to this ICST Artist Talk with Philippe Esling. Philippe, thanks for being here. Let me just give you a very, very short introduction. So I'm really happy to have you here. Thanks for coming. Philippe is a leading researcher and artist at the intersection of machine learning, artificial intelligence, and music. He studied mathematics and computer science and has a PhD in genetics. Postdoctoral, sorry, my bad. He's currently associate professor at IRCAM and Université de Sorbonne. Also, he's the head of the ACIDS team. ACIDS standing for Artificial Creative Intelligence and Data Science.
Absolutely what it means.
And he teaches computer science and mathematics at Sorbonne University and machine learning at the IRCAM Masters, which stands for Acoustics, Signal Processing and Computer Science Applied to Music. And he's recently been appointed as professor in Tokyo University. I hope that's okay. Yeah.
Yeah.
And where you will start teaching in January. Yeah. So we are really happy to have him here now because I think it will be a bit more difficult in future. But I hope this is not the last time we have you here. I can give you just a tip of an iceberg of activities of Philippe. I think his work is consistently building bridges between science, technology, and the arts, and that's a really great achievement. And probably you've heard of RAVE, maybe after, which is becoming quite famous or is famous. So that's I quote that, a variational autoencoder for fast and high quality neural audio synthesis. It allows you to work with audio in real time using AI. Also, you built something that is called the Flow Synth, which builds a bridge between a synthesizer and audio input based on AI, letting you then work with the parameters. And you've been also doing a lot of research in musical orchestration in connection with AI. And I think there's a common ground with all these activities that points toward timbre, and I'm sure you'll give us more about that today. And I warmly invite you to look also up his GitHub. There's many other things you might discover. And yeah, the talk will be for about an hour, and then you have time for questions and answers. And so, tomorrow is also the workshop starting at 9 o'clock. If some of you, by any chance, want to participate but haven't written to me, please do so. All the others have been accepted. It's a unique chance to work with Philippe. Now I give you the word, and thanks so much. Warm applause for Philippe.
Thank you. Well, what an introduction. I mean, I'm blushing now. Thank you, Misha. So thank you for the invitation and thank you for having me here. It's a real pleasure to be back after a year and a half where I presented some stuff. So actually when Misha invited me, I was kind of ashamed of myself, thinking, oh, I'm not gonna show the same stuff I showed a year ago. People are gonna laugh, so you need something new. And I realized there is a lot of things that has been going on for the past year and a half, and especially the relationship people have with what's called artificial intelligence, which is now. You know, I said that to Misha earlier. 10 years ago when I said, oh, I'm doing AI for music, people were like, what the fuck are you doing? And then 5 years ago it was, wow, so amazing. And today it's more like, ah. And you know, there's this feeling of unease somehow. And I completely understand why, and I agree with them. That's the worst part. So I realized I wanted to make a weird presentation today, so forgive me if it's gonna be a lot of personal opinions on what I feel might be a different way to look at the problem. So I want to start with something where I'm not an expert at, which is called organology. So it's basically the study of how musical instruments were developed. So correct me if I'm wrong, but I think we all started by just hitting on stuff, right? We took like objects and we started pounding and seeing, oh, this is funnier than this one, right? So you can find traces of that until we started developing this kind of system of melodies, and we basically iteratively took objects and changed them up to the point where they would produce the right sound we wanted. So it was basically physics that was shaping the constraint of sound. So we had to change the physics, the nature of the object, to change the audio itself. And you can see, for instance, the violin, I love this example, comes from the rebab, which is actually an Arabic instrument. And this went on like for a very long time, where we started saying, oh, technology is shaping music somehow. You know, the science was there in the form of physics and material science. And then there was this big shift in our perception to how we can create audio, information, or music with the appearance of electricity. And electricity kind of sparked a lot of development, being either analog or digital. For me, it's kind of the same. We get rid of physics. We get rid of this constraint of having to shape the object, to shape the audio, and to shape the control. And now it's kind of the opposite way around. We have to find a way to control this thing, which can do a lot of sounds. And it seems that we are disconnected from this idea of producing a force which allows to react by the means of our force into the audio domain. And now, today, we're arriving at this point where there is this weird thing called, I like to call it not AI, but neural audio synthesis, which kind of allows me to take some distance with the saying, no, I'm not in AI, you know, I'm in neural audio synthesis. Sexier, right? And also the fact that it doesn't bear the same crushing aura of something that is going to replace us. And my big question was, how do I create new controls with this thing? How do I use a system which is basically way too complex for myself, and I don't know, maybe for others as well? So just to take the way it works, of course, everybody knows you take a lot of example, feed it to the model, and then you create stuff. And there comes the problem, is what do we do? How do we control this thing? And everybody is yelling at AI in the sense that, yeah, it's not artistic because I can't do what I want. And people all think about the same thing, which is, oh, let's put controls in the form of a MIDI score, of the type of instrument. Let's do stuff that we used to do. Let's take our known concept, and even worse than that, let's put language in there. You know, and language is the worst idea you can have with an instrument. That's how you get into creating some evil that you should basically get rid of, maybe one day, I hope. And there is another way of looking at that, which is, instead of trying to take this thing and bring it back to the realm where which we feel we have power, let's just forget power. Just think about the fact that there is ways of using this to also discover concepts from the data itself. And it's creating stuff that we can't understand and we can't label and we can't like say this thing is this button, does this thing. Yes, so what? I mean, I have a beautiful example of that, which is rave. Not trying to preach my own quo. I'm not sure of the English way. Prêcher ma paroisse, sorry, I'm French. So, anyways, so for instance, like everybody might know rave, so you take a sound, turns it into something like a voice, but the cool thing is in the middle, you can just put a button, right? And when you turn this button, it does stuff. And the other button does other stuff, you know? So what I'm trying to say here is that this presentation is going to be a weird plea for the concept of transcendence as a new objective for AI learning, and why should we aim for that? So of course I'm ready to get roasted, and I would love you to roast me, because a lot of people have roasted this idea. Philosophically, a lot of people say that it's completely useless. You know, a lot of thinkers and philosophers say, yeah, there is this absolute limit of our knowledge. You know, if you look at Blake, for instance, he says like, mankind can't reason about things that you have not perceived yet. So human cannot reason about things they have not perceived. That's something I ask my students the whole time, like, can you create a new animal right now? Dramatic pose. is there anyone in this room able to create an animal which is not just a combination of two animals or two concepts that are part of the previous perception? No, you can't. I can't. Nobody can't. Nobody can, sorry. So what I'm getting at is that there are thoughts and ideas that escape the use of language, can even escape our own perception. And of course, if you listen to Kant and Wittgenstein, they will say, on what we cannot talk, we should stay silent. Oh, thank you. And Sartre, which says the relative is unthinkable. I mean, yeah, of course, I agree. Like, I can't talk about things if I don't have the words to talk about them. But it might be philosophically useless. Does it mean that it's pragmatically usable? So my idea is that if you think about FM synthesis, for instance, I don't know if everybody knows FM synthesis here. Yeah. So frequency modulation synthesis is kind of a big box with a lot of buttons. Those buttons, they are named operator 1 frequency, operator 1 level, blah, blah, blah. You know, they have like names we can understand, but if you turn it, my God, this thing does wild stuff, right? And we can't predict how it's gonna work. We can't like imagine what's gonna happen if I turn this button, which is exactly the same principle. It is not because I cannot name it that I cannot explore it. And like, with a bigger scope, is it not what we have always been doing in music? Like trying to discover stuff and say, wow, that's surprising. And then later on, figuring out what the fuck just happened. Let's find a word for that. You know. So basically what I'm saying is that we should stop trying to do text to stuff, and basically non-semantic controls are the key for exploring. And second big concept is like not reasoning about something and not using something are two different states of being. And finally, which is kind of different, but I wanted to shove that argument in there. If it cannot break, it cannot transcend. Like if an instrument cannot sound bad, then I think it's not an instrument, right? I know it's weird, you're like, what are you saying? It's just that these things that always produce a good output for me is problematic. I want something that sounds bad and I want to get better at it, right? So that was kind of the idea. Now it's talk. How do we get there? So what I'm saying is that there might be two ways of looking at controls. Like, I'm not saying let's trash everything we've been until now, AI is the new God. It's like, no, absolutely not. There is stuff that is explicit, right? There is description of sound that we know, even like mathematical description, like centroid, like, I don't know, fundamental frequency and this kind of stuff. There is like, you know, explicitly created representation like MIDI. That is amazing. So that is very precise and it allows a very like natural control of some stuff, but you need to have a definition, a word where everybody agrees on the terminology. On the opposite side, there might be this other world of what I like to call implicit controls. So implicit controls are the rest. You know, the thing we don't know exists. We know it should be there, but we don't have a word for it. That's the kind of thing that Rave does. And it's quite amazing for me that it's a whole new world of interaction, but it's very hard to integrate in the way we create music and how we've been creating music up to now. And I think there is actually a whole continuum between those two worlds. It's not like there is a solid line separating both worlds. So my proposal is, I think we should rather try to combine those explicit and implicit control into generative models, not necessarily AI. Of course, I'm doing AI machine learning, so I'm going to show like a machine learning approach to do that. But the idea being that we want to generate using both things that is explicit and things that is implicit, and we just need to keep those two separated to do so. So, another thing I want to convince you, and that's part of my usual presentation, I still have some slides from the last time, I'm sorry for those who saw that. I want to convince you also that a way to look at machine learning is just a question of space, because music lives in different space, and I'm gonna use the term space a lot. So basically you can think about, for instance, the waveform, which is the domain of acoustics, and the spectrum, which is the domain of signal processing, and the symbolic score, which is the domain of computer music. And if you go one way, you're kind of trying to understand something. So you're trying to like get information out. And on the opposite sense, you are trying to generate. So the problem is, how do we transform from one to the other? and how do we transform to a different space? Basically, this is what we've been doing like in the past with music, and we've basically been doing something very simple, which is compressing and decompressing or comprehending. So for me, compression is comprehension in this kind of problems. The problem is that we are going to compress to something that we don't understand and we don't have names for yet. So this actually is something you find a lot in the machine learning literature, which is basically if I take a very complicated space and I find a way to transform this space into something where relationship between different parts of the space make more sense, I'm kind of unfolding the original space to its rightful shape. I'm going to take a paper. I love this. I don't think I did it. It's something I do to my students, and I always love the wow effect. So how many dimensions is this piece of paper? I did it last time. No? Yes? Oh, damn. Damn. I'm getting old, you know? Just repeating. Anyway. So for those who weren't there a year ago, so how many dimensions is this piece of paper? 3? Why 3?
There's a thickness, huh?
There's kind of a thickness. But like basically I can't travel along the thickness from this perspective. So we want to say 2. Please say 2. Thank you. 2, absolutely. The man on the back. So now, how many dimensions is this object? Effect. It looks like it's 3. Like, right, it looks like 3, but it's just that it's a simpler space, which is called embedded inside a more complicated space. So the goal is to find a way to unfold it to its original dimensionality, which is a new way of representing the same data, which is the goal of representation learning. And so this is kind of the way we make it also for audio. So we basically take audio, and this audio we're going to try to compress it or unfold it. So of course, a way to unfold it would be to things we know or things we don't know. And this thing, we called it latent. So basically latent comes from the Latin latens, which means hidden. So it's just hidden information. And from this hidden information, we're going to try to generate back from this to the waveform. So basically what we obtain is the structure of what's known as an autoencoder. So an autoencoder means you encode and decode the information, and then you can basically compare the input to the output in order to learn what's in the middle, which is called the latent information. So if you look at that, on one way it looks like we are trying to understand or compress, and on the other way we are trying to generate from this compressed information. So the whole question is, how do we control this thing, and how do we create new types of musical instruments? And that's basically what we've been trying to do in the ACIDS project. So ACIDS stands for Artificial Creative Intelligence and Data Science, which basically is trying to use both theoretical and applied research for musical creation. And most of it was based on this general idea that we are trying to find spaces where musical information can be simpler to control or provides new way of controlling the same information. So we have a lot of open source. Everything that we do actually is open source. It's free. You can go and download it. So maybe most of you know Rave or FlowSynth, but we also have 3 new things. So I'm going to quickly show Rave and Tilde, since it seems most people know. And I'm going to show these 3 new things that we've been working on the past year and a half-ish, something. So basically, if you go to GitHub, you can find FlowSynth, you can find Rave, and you can find Tilde. I'm just noting here that people confuse a lot Tilde and Rave and think it's the same thing. And tomorrow, the workshop is actually dedicated to showing that you can take any model on GitHub, like source separation stuff. You can take, like, I don't know, like a clap or stuff that just produce annotations. And you can put it inside Tilde. And I'm going to show you how to code that, which is basically, this is a host, right? It's kind of like VST, but for deep learning models, which is the interest of it. And we just pushed recently the 3 new things I'm going to show you today, which is After, which we're going to see is trying to target this idea of implicit and explicit control. And we have the thing called Rave Table that I'm going to show also today. And finally, Torch Bend, which is quite an experimental thing for neural bending on audio that I'm going to present also today. As Misha brilliantly said, if you want, you can check on GitHub, because I did a lot of work on the pedagogical aspects, because I feel a lot of the fears coming from machine learning is actually people don't really know what's going on. And so that's why all my courses are also open source. So there is a huge course on machine learning with like all the theory, the math, and the exercise on how to go from zero to hero. I mean, zero to coding, everything I show you. Like the end project is kind of redoing Rave and knowing all the math on the way. There is also like a course which is more for musicians that want to use all the stuff in MaxMSP and how do you code this to use it yourself. So yeah, and there is a lot of tutorials as well, like on normalizing flows, diffusion models. So please go take it, it's free, enjoy. Anyway, so really quickly, let me recall what is Rave. So Rave is a variational autoencoder, so real-time audio variational autoencoder, which we did with Antoine Caillon, which is now working for the Magenta team in Google. And basically the idea is exactly what I showed you. We compress and decompress. The kind of smart thing about Rave was to split between 2 stages, one where we learn this representation and we don't really care about the quality of the audio we generate, and a second stage where we stop, we freeze the representation, and then we fine-tune the quality, which was the key to having a very small model while having very good audio quality, because we separate the idea of compressing and the idea of decompressing while still having the same like workflow. So it is high quality, 25 times real time. The most recent thing we did work on a Raspberry Pi 3. So I'm going to show you at the end. We are now working, we have a hardware synthesizer with Rave. Like actually the company that kind of developed, it's called Newton Cosmo. They did a thing that is now a project with Roland, and they are doing like this little pedal. It's a Rave pedal somehow. It's like kind of an audio effect, real time. And it does this magnificent thing, which is timbre transfer. So interesting thing about it, we didn't make it to do timbre transfer, but it was doing timbre transfer. Crazy, right? Just because it's too stupid to understand anything else. Because it's so small, I mean, since it's small, it can't recreate every audio you give. So it's just recreating what it knows by reminiscing of stuff it's seen. So if you do a bigger model, it won't do transfer, which is the beauty of it. Like the big property of it is actually why it does the other big property of it that we didn't want, and just end up with it, and we were like, wow, that's so cool. So yeah, just a quick, that's the first example. It's not there. Anyways, I have other examples. I can skip. I forgot to download the sound samples. Don't worry, I have the real-time version. So this thing is available for real-time MaxMSP. It's also available in Raspberry Pi, Jetson. You have everything online. And recently we had like this kind of artistic tsunami of stuff. So like last year we worked with Bjork on a project at the Pompidou Center. There was an exhibition by Olli Andon, which uses the new version, which is called After. So I'm going to actually show you the model that was exhibited there. We retrained it on a different data set because Holly went around the UK to record choirs. And so we did a second model on like kind of open source choirs to be able to distribute it. And the cool thing about Rave is that it's also used a lot in like electronic music, like clubs, festivals, and stuff which is more related to, you know, let's say pop music. I don't know how to say. So that's like a big success for us, the fact that this thing is really useful to artists and that it's creating actual pieces of art that are different from what we used to see or hear, which is the whole point of it. Not imitating, but really transcending. So now to move on to what we've been doing lately, so there is a big kind of trend in this idea of neural audio synthesis, which is basically that the things like rave and all of this can be seen as what's called a codec. So codec just means compress, decompress, right? So it's just a way to, pass the audio as a zip file, right? So the latent is kind of zipping the audio information. But if you look at what's in the middle there, you discretize it, what you obtain is a series of tokens. And this series of tokens, of course, works perfectly well with transformers, which leads to model that I'm not a big fan of, but things like music LM and this kind of stuff. And then you can actually generate. So it's kind of interesting because you see these small spaces as being a way to do a first step of understanding, and then you have another model which learns how to generate from there. So basically the second model has less thinking to do. So you kind of capitalize on this idea that you have a better representation space, and basically this allows to kind of see that as a more semantic information. Recently there's been a post by Sander Dilleman which shows that this thing actually in the middle can be seen as kind of glorified audio windows, or for image, glorified pixels. It's just a pixel that encodes more stuff about its context and the things around it. So basically what you have is a better image. And that's what we've been kind of working on, this premise of thinking, okay, what can we do to capitalize on this idea, which is basically we want to train something of higher level information, still capitalizing on this unknown implicit controls that we just found. So basically the idea was, can we use this kind of hierarchical thinking to train a latent generator to learn patterns based on the data? And so I don't know if I should introduce you to the wonders of diffusion models. Everybody knows diffusion models? Do you want to see what's a diffusion model? Let me show you a diffusion model. So basically a diffusion model is this idea which is, let's take information and then gradually noise it. So we add a little bit of noise, and each of these steps is actually just a little jump to a little bit more noise. And I can go on and on and on until the time where I'm basically having only noise, right? Just by adding these little steps. So that's called the forward process. The forward process actually mathematically goes from the distribution of data to a tractable distribution, which means a distribution we know the mathematical form of, right? So now that we know the form of this distribution, what we need to learn is how to go back to the distribution where we don't know the form of that distribution. But since it was just by doing these little tiny hops of adding noise, it just basically removing those tiny hops of noise. Originally, that was defined as this idea of what's called a Markov transition kernel. So what you see here with like this glorious Greek notation is actually just simply saying going from one step to the next. The problem is that this takes a lot of time, and recently it's been extended to the idea of ordinary differential equation, where you see this path from one distribution to the next as being the differential equation of moving from the original distribution to the end distribution. Okay, see, that wasn't that complicated. So now, what can we do with that? So originally my idea was, still, let's try to find a better way to understand what's going on in latent space. And basically, I asked myself, what's the problem with Rave? Rave is amazing, it does a lot of stuff, but it's kind of compressing everything at once. And it doesn't have this way of separating what's explicit and what's implicit, or more simply, it doesn't know how to separate the structure and the color of what I'm giving it. So I'm saying structure and color because you can think about it as structure and timbre, but I don't want to say like MIDI. We can say MIDI, but this is to simplify the idea that we don't know what is timbre, okay? And basically in some scores, you have scores that contain different elements. So basically, if you take a drum kit and you change the drum kit, you're changing the color. But if you change the notes, you say hi-hat or you say Charlie, it's not going to say the same thing about the color, even though it's a symbol, right? So what I'm trying to say is that the score itself might contain information about the color that we don't know about. So the motivation was, at least, can we try to separate information into two? And how do we do that? Basically, what we're going to do is we're going to say, let's start, of course, with rave, because we love rave, and because we know how it works. And it does this compression, and we have this better representation. And now that's the point where you have to follow a little bit, which is, let's first try to learn something on the premises that how do I talk about color or timbre or something that is representing not events. I'm going to say timbre is going to be things that are not moving through some period of time. Okay, so I'm taking a point, I'm saying what's around should be the same color, right? Then I'm doing exactly the opposite of what was done in the definition of timbre. So for those who don't know the definition of timbre, timbre is everything that pitch and loudness is not, which is saying timbre is the negative of pitch and loudness. What I'm saying is the opposite. Structure is what timbre is not. Okay, so everything that moves through time is structure. Everything that does not move through time is timbre. So basically, we start by learning this first encoder, which is a timbre color encoder, which basically maps to something that has no time dimension. So we take something through time and compress it to something that has no time. Once we learn that, we learn the second thing that has time and say you have to learn something, and we use this gradient reversal thing, which actually says you have to contain information that is not on the second part. So it's just remove time and find everything else, please. Okay? So this structure encoder is actually what makes the whole thing of finding a way to separate the information. And so this work was done with my amazing PhD student, Niels de Merle, which is still working. He just finished his PhD and graduated with honors. All hail the great Niels. Anyways, and this thing is available in MaxMSP already, so it's kind of the same for those who used Rave. We now propose After, which still works the same way, but with more latency because we split the computation even more. So basically now what you can do is actually you can split between timbre and structure encoders. So basically you have on one side an audio information or MIDI, which is the new big thing. We can now pilot this thing through MIDI. I'm going to show you both in a few instances. Or on the right side, you have the timbre, which is the color. Or you can directly control the color with the structure moving on the same way. Then we expose the latent diffusion model. So you can still do, from this point on, all this thing is exactly the same as Rave. So basically all these connections there is the same as the Rave connections, right? So you can go low level or high level if you want to. This thing is on GitHub. You can train it yourself. Tomorrow I show a bit how to train it. We have models, blah, 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 blah. Let's do a demo. I'm getting tired of hearing myself. I'm sorry, it happens. Well, I forgot to stop it. It's been running in the background. No, I'm stupid, it's me. So this is the MIDI. So now it's generating in real time. I can of course change it to, and you can see it's kind of, sorry, is it too loud?
No, I won't change it. Go ahead.
Oh, okay. So you see, you can pilot this thing through MIDI. And of course it's adapting to the register. And then you have the second part. So what you have here is feeding the structure encoder. So I can do something like, for instance, arpeggiating. And now I can move the color, which is basically the type of voice. Okay, another example which is purely, so this is both MIDI, whoa, yeah, it does that sometimes, don't worry, it's transcendence. So here is a typical example. So now I have no MIDI, I only have audio. So this is the input, and I have a model that has been trained on this model has been trained only on on drums. So the cool thing is I can now change the color of these drums. So you see, here it's heavy intensity, this yellow part. Can you see the thing? Like I'm moving on this map. So the blue part is glitch. It's a friend of us that does a lot of glitch. And you see, you keep the structure and you keep the tempo, but it's basically changing the color of the thing. So this is more acoustic drums. Around here, the green thing is acoustic. And now, the amazing thing, my favorite part of it, remember that we split structure and color separately. And basically this means we have the same type of implicit weirdness as rave on the structure. So for instance here, you see I'm very steady on the color and the structure, but I'm gonna mess up the structure. And I'm gonna say, I don't really know what I'm doing, by the way. I'm turning stuff randomly, so, but you can completely change, and still, you see it's starting to do like, it's still kind of rhythmical because it's still fed by this thing. This is the input, but then I can bring it to like a completely different realm. I'm gonna stop because I could play with this stuff forever.
So the previous question concerning user interface, so why did you decide to use knobs for the structure part and this 2D map for the color part?
Excellent question. The thing is, here we have some way of linking an information which is the color and the labels, right? Mm-hmm. So we basically here have something that has no time, remember? So basically this is compressed. And so it means one point means one color, while this thing evolves through time. So for each of these knobs, we would need actually a temporal representation. So if we were to represent this, that would be a set of signals. I can show you my rave device, it would be clearer. Mm-hmm. Wait, I have this other thing I wanted to show you later, which is the last thing, rave table. But anyways, so you see it would look like this for each of the knobs. And each knobs multiply or add something to the signal. So we either multiply or add. So basically, if we represent it, it's just to say, hey, look, it's beautiful. I don't think it's, as a user, that's an excellent question, actually. I would love to find a way to make it more kind of...
More navigatable.
Yeah, exactly. Yeah. Exactly. But each dimension is a moving signal. So then the knobs themselves, they just multiply and add to the signal, which for me makes it weird. I can show you it wasn't planned, but let's do it. Hopefully it doesn't mess up my whole demo, which was going perfectly. Experiments, where is it? It's this one, demo old, devices. I'm quite organized. I'm actually surprised about that. Rave, and let's take, yes, this one. So for instance, this is a Max for Live I did for Rave. And let's take, I don't know, 303s. I have so many models. My life is models. I don't know, I took a random one because it has a, so you see, that's the kind of information, the latent information is this. For instance, let me use the prior model.
It's ASMU.
So this one is just generating itself stuff. Actually, this prior model is not really good. Let me take Will, which is better. Don't crash, please. Thank you. No, it's never crashing. So basically here, like the scale button, that's typical rave stuff, right? And basically that's the same, these buttons right there. So if I was to represent the structure thing looks a lot like this. That's why I was saying there is a lot of implicitness in this thing, because I can show you the thing so you know, oh, right now I'm going down or up. Well, it's really purely beautiful. I don't think it bear any controllability to it. Okay. Anyways, so yeah, and the cool thing with this thing, so let me show you, is that you have also like this big scale thing, which is just scaling everyone or biasing everyone. So now you see I completely destroyed the structure. So it's amazing for sound design, but I can reset this thing, and supposedly it should. I can restart and I can, but I'm not sure what to represent here. Okay, let's move on, right? I only have 15 minutes left. Okay, let me skim through, at least to show you the last things I wanted to show you. So TorchBend, unfortunately, I don't have a demonstration, but it's kind of a cool idea, which is dissecting and bending generative models. I don't know how many people here have tried this thing, which is called circuit bending, which is basically you take a children's toy, you open it up, and then you try to randomly plug some stuff in to just mess up the way it works. So you're basically forcing this thing to do stuff it wasn't planned for. And of course we wanted to try the same with neural networks, which is basically, can we just mess up the inside of a neural network to make it do stuff? So basically what we do is we expose the inners of the neural network, and then we apply destructive operation with the idea that destruction is creation, as we said earlier, which is basically how do we make the networks extrapolate, so create stuff they were not meant to do. I will show you examples later. So basically we do that by injecting inside the weights and the different, so the weights are the way the network compute the transformation. So we just apply transformation here, or you can directly change the operation in the middle of the thing. So in the activation, you can also mess up the way it works. So we expose those two things. You can find this library online. So it allows to do like very weird thing directly. For those interested in image, Axel Schemmler, which is the creator of this toolbox, did touch designer object for image. So it basically allows you to mess up StyleGAN, which is generating image. I can show you outputs, and it's just like, yeah, you have the eye is going in the middle and starting to. Anyway, beautiful stuff. Okay, any question? I'm sorry, we're on a.
Question later. We still 15 minutes. And then
Yeah, I know, but I have so many stuff. I have also 2 demos left. So, anyway, so this thing is available online, and I just want to take a bit of time to show you my little baby, because it's the thing I've been kind of passionate about recently, and I mean, I kind of didn't work on it for the past 2 months, but it's still very relevant. So we've seen a lot of approaches that are like, they all hinge on this idea that you still need something inside, right? You need to give it something, so it answers to your something with something. So which is the whole point, yeah, of course, of auto-encoding. I encode, I decode, cool, I learn stuff, and then I get audio. But in fact, in the middle of this thing are something that is usually called latent space, latent codes. And how about we start saying that this is a latent signal and not a latent space or a latent code? It's actually a signal because it is a signal information. We are compressing it through time, but it still bears the same principle, which is numbers that evolve through time, which is by essence the definition of a signal. So the thing is, if we look at these things as being first-class signal objects, we can basically treat these things as wavetables or array tables. Yeah. Anywho, so basically the idea is that, for instance, if I use a table, I can kind of, memorize this table, save it. I can then save a second table. So this first table, of course, I need to decode it to obtain an audio. And the second table, I can also decode it to get a signal. But if we kind of hide the idea of decoding and just look at what's up there, basically what we can do is we define operations on this level, and we can use everything that has been used for wavetables, which is morphing between tables, looping, applying frequency modulation to those tables, warping those tables, and of course doing any form of DSP operation directly on the table. The only problem is that the DSP operation you apply here has absolutely no relation to the DSP operation you apply here. Let's think about it for a second. What is a low-pass filter in a latent signal space? I'm doing the timer.
Slower change?
Exactly. It's kind of MFCC idea of basically what you have is you're filtering the speed of events. You're not filtering frequencies. It's like if you take the FFT of a FFT, what you get is you get like speedy things and slow things, right? So if you apply a low-pass filter on the latent signal, you're basically removing like speedy events or fast events. And oppositely, if you apply a high-pass filter, you're removing things that go slow. So super interesting, right? Because I had this idea that basically what we've been doing over the past 50 years with signal processing is mostly, I don't know, we take stuff, we destroy it, and we say, that sounds cool. You know, distortion is basically applying something which is destructive to a signal. It's just clipping it, or, you know, and we're like, oh, more harmonics, nice. But there is no mathematical reasoning behind that. Like, why did we apply distortion? Because it sounded great, right? So I'm wondering, I mean, it's very, in its infancy, I just did a small like demo paper at Izmir 3 months ago, but I already produced this device that is, of course, open source and free to use. And it's called Wavetable. And there are 3 major components to understand the use of this new thing, which is basically, number 1, you get the source creation, which is you need to still create these series. At one point, you need a way to obtain the tables. Okay? If you think about Serum or something like that, what you do is you take a piece of audio and you chunk it. It's not coming from nowhere, right? But then you have a player, and this player is actually exactly like a wavetable synthesizer. It has those small tables, and it's going to loop it forever. And then you have this whole idea of applying weird effects to the wavetable thing. So basically, you can kind of mess up the sound. If you are happy with the sound, you can save it, and then you can restart from there. And basically, so the general workflow for using the model and recording tables is that you have a source, and this source is kind of the information generation stage, and you have the recorder. And the cool thing of the recorder, as you can see, is that it's beat synchronous. So of course, wavetable, they work on a time span that is way bigger than classical wavetable. It's not like a single cycle loop, right? It's kind of more 4 beats or 8 beats. But then I can do all the weird thing I'm doing usually. And I'm going to skip through a lot of things because I want to play. But basically what we're going to see together is what does it mean to have like this second section. Once we created the table, we're going to create a few tables and play with them. So once you have your table, you, with this player, can, for instance, morph between 2 different types of tables, and you can of course mess up with the way it's played. You can inject some FM synthesis inside your tables. The FM here just means like the table itself is going to be FM'd, so it's completely different once again. Let's stop talking and demo time. Yeah. So that's where is it? This thing called Wavetable. So Wavetable starts the same way as Rave, which is basically okay. So for instance here, I'm actually giving this thing. Okay, and the problem, as I said, is what can I do with this in the typical rave world or latent synthesis world? I can apply a filter, for instance, and I can say I'm going to filter the input. It changes the way the model reacts. But then I'm kind of stuck, you know, I can mess up a bit more the input, not satisfactory. So what I can do here is say, okay, I like this, so I'm going to record 8 beats, and I'm going to push this to this table, and now I'm going to shift to the table, And you see, I don't need an input anymore. And now the cool thing, I can actually take a part of the input. So now I'm kind of slowing down time, and I can, of course, say, okay, I'm going to take a super tight loop, and I'm going to make it faster. I can make it even tighter. And I can scan through my wavetable saying, let me... Okay, I like this loop. Let's say I like this loop. The cool thing is that actually the recorder here, it's recording all the time. So what I can do is I can now push this to the second table. I have to come back to the normal setup. And now the thing I was doing right before, the thing I was doing right before is now in this table, and I can morph between the two. And of course, I'm going to have something in between, and I can load some stuff because it's wavetables. So, for instance, I have one here which is a bass or lead drive. Sounds good. So, that was something I did another time, which is, it's kind of, I passed the bass, which is something like, you know, typical dubstep stuff. And this is the voice model. But now I can morph between this and the rhythm I was doing. So I can kind of, you know, explore different ways of working with this. And of course I can still do this too, which is, let's say I like the beginning. And let me put some effects. I have no idea what's going on. I got lost. Why not? Anyway, the weird thing is also, I discovered something very weird, is that if you put the tables from a different model, that's a model that I train on electricity. I can make you listen to it, like my favorite model ever. So it's basically doing electrical arcs. So not now, but later I will put some electricity. And if you take the tables from this electrical model, it still does. I have no idea why it still works. It's doing completely messed up stuff, but I can play with the tables of one model to kind of use on another model, and I can kind of morph between those stuff. Anyway, this thing is funny, I'd say. That was the point. Well, thank you. And I still have how many? I still have 43 slides. So I'm gonna thank you for your questions. Now it's kind of what we are planning next. Maybe I'm just gonna skim what's interesting in there. There is a lot of talk about Occam's razor. Sorry. Yeah, this is a big problem. Like, why do we do stuff on these big servers where we should be doing stuff on these small things? And that's why I think we should reverse the trend. You know, instead of going this way, why don't we just come down this way? That's way more interesting. And also a model that uses basically the electricity of the whole state of Congo is not smart. Right? Like, that's not my definition of intelligence. It's just a bulldozer. There's no fucking point. So basically we've been working on that, on this idea of trimming the models. So basically we use a model that has been trained on doing a lot of things, and then we just basically kind of fine-tune it by, it's a mixture of destroying part of the network, but destroying the parts that are not used for a specific type of sound. So we train our model on lots of sound, and then we say, let's look at what reacts to only this sound, which allows us to kind of trash everything that is not doing this specific sound, which allows us then to kind of remove all of these parts of the network, which leads to a model that we managed to put on this thing called junk. It's David, my PhD student. I don't know how I can find those students. They are just magnificent. So he wanted to call it junk, and I said, okay. So yeah, beats me. Like, it's not an acronym, by the way. It's just, he said it's a big piece of junk. I was like, okay, not very sexy, but why not? Sorry?
Who's the PhD student?
David Genova, sorry. It's like the first author of this paper. Oh, I didn't put his name. Okay, sorry. David Genova. And he's also the creator of the amazing junk synthesizer. Let me put attribution where it's due. And we used this with the composer Piers Warnecke recently. It was really cool. Stuff. Yeah, that's kind of what I was talking about when I was talking about bending and creating stuff that is outside. So this is, for instance, a thing we did 3-4 years ago. And I'm still excited about the idea, but we never managed to make something better than that. So maybe one day. So it was an image model trained on NIST. You know, NIST is the data set with digits like 1, 2, 3, 4, 5, 6, 7. And I had this weird idea, like, how do we make a model that knows how to do something go outside of what it knows? And most of the time, if you ask that to a network, it will run through noise. Like in 2 iterations, the thing just throw out white noise, because, you know, if you go any direction outside of the distribution, just noise. So my idea was, how about we ask it to optimize the whole distribution, but avoid the sub-distribution of each digit. So basically, you have the distribution of all of NIST, and inside this distribution, you have the distribution of 1, you have the distribution of zeros, you have the distribution of 3s. So the objective is generate something that fits in the whole distribution, but is different from every sub-distribution, which is a fucked up problem, right? Do something that is a digit and is not a digit. Or do something that is a digit but is not 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's what you get. Kind of this alien language stuff. So I love this idea, and the idea would be, can we do the same with like more complicated stuff, which is this idea of bending. We do a lot of music, and we have a lot of collaboration. We have a Discord, and we are starting an artistic collective. Please contact us. Thank you all for staying with this weird presentation the whole time, and thank you. Yes?
I have a question with the after model concerning the separation of what is like the time invariant and which is like independent of time. I mean, maybe it's very clear in the, let's say, sound domain, but naively for me it's a very philosophical question. What do you decide to identify with itself through time and not? For example, I can say that I'm changing, I'm a different person which I am today and tomorrow, or I'm still me. So in the case of audio, or in any case of what you decide with data, what do you say is unchanged, or you define as unchanging, and what not? Is it like, is there preference on what is more learnable? Is it a preference on what you want to control?
No, that's an excellent question. Actually, I don't have an answer, in the sense that that's the closest thing we found to manage to separate color and like time evolving and time static. But we tried it, for instance, we tried weird stuff. Like what I showed, the choir thing, I think it's less than 6 seconds, it's like 2 seconds or something. But since it's choirs, and we have like hours of a single choir, like singing a lot of stuff. So it's the same people singing different stuff. So basically, in that sense, you are kind of, if you think about the like distribution of what you're seeing, kind of makes sense that it's the same color, in my sense. Of course, the problem is what is a good time scale. I think that's the whole essence of the question, which is basically if I look a millisecond after and a millisecond before, supposedly it's the same color, but at the same time, maybe I'm sitting right on a transient, right? So there is no absolute best answer to that. And we tried weird stuff, which is we fed whole musics, like the whole piece of music, and said, this is one color. And it's basically then becoming the color is more the genre, maybe. You know, that's why I don't like the word timbre here, and structure is just kind of something that is independent of the events across a certain time scale.
Yeah, but for me it's a bit of kind of like walking around the question. I mean, for example, this when you say time scale, it's already a very specific definition of what do you want to collapse into a self-identification or not.
Mm-hmm.
I mean, you can choose for whatever you say that, I mean, you can, yeah, like whatever you say that it changes over time or not. It depends on what you define of differences. You can also have singing voices, and you can have say that the singing voice is static because you use voice at all. And then you just identify every voice with the thing which stays, or you say that the tone of the voice changes, so it's not static anymore. So
Isn't that the tragedy?
What is static and what is not is for me very elusive.
Isn't that the tragedy of Western science in general? Like, we take something that is constantly moving, a wave, and we say we're going to cut it in small chunks, and we're going to call our buddy Joseph Fourier, and we're going to say, hey, how about we turn that into a set of vectors? And in itself already, we are kind of moving away from the true nature of continuous information, which kind of precludes the several questions like, is there anything that is truly continuous? Or are we always trying to create a taxonomy and cutting into... I'm not saying I have an answer. I'm saying nobody has an answer. So there is always a point where you need to make kind of a decision on this is... When I said time scale, I was saying, let's say, time horizon or receptive field, whatever you want to call that. It's kind of you take the decision that you're going to state, this is color to me. And of course, it's restrictive, it's completely elusive, it's far from perfect, but it allows you to separate things into this moving and static approximation, right?
And the last question, the other, do you think there's a way to do it somehow like unsupervised, that the model itself decides on some criteria what makes sense to collapse into what you would call time static?
Yeah.
In the sense, I don't know what it's easier for the model to compress and what's not, and so far and so on.
Yeah,
So
I just realized, I think it's fate or karma, I don't know how you want to call it. 3 months ago, I was a jury at a PhD thesis, and I asked almost the exact same question to the PhD student, and I thought, I'm so clever. And like he was, I have no idea. And I realized now the universe just threw back the same question at my face. So good thing for me. So I asked him something which was related, which is it possible to do something called self-unsupervised? Which is basically what you do with self-supervised, which is saying, I'm going to take something which is unsupervised, and I'm going to create a pretext task. And this pretext task is going to help me learn by creating supervision, carving supervision inside unsupervision. Even unsupervised, if you think about it, it's not really unsupervised, because we're basically putting reconstruction in there as kind of an excuse to learn stuff. So I'm actually now in the point where I'm jiggling around the question, saying I have no fucking clue. But basically, it's like you always need some form of question, right? That's the whole premises of machine learning. Learning means you have an example, but you also have a question to ask, which can be optimized and represented in terms of a number that can decrease. And of course, if I wanted to say right now, what would I try to do would be to do something which is what I think people that don't know what to do are doing, which is basically trying to do that on a lot of different time horizon and trying to have like a whole set of model which would kind of span the different properties in terms of time and other dimensions, for instance, frequencies and time, and do some form of hierarchical model to try to find which one like minimize, for instance, the entropy of the, I would say maybe if you use, mutual information between, mutual information, which is, I think it was shown in the information bottleneck theory. So basically, if we kind of tried to generalize across time scales and across frequency scales, we could measure the mutual information between VT and X and then say, let's pick the one with the biggest mutual information. That's kind of bulldozer approach, but it kind of generalizes across as like different, it kind of gets rid of the problem by creating all the problems. That's my lame answer, sorry. Any more questions?
Maybe hopefully a simple question. In the example you showed us where it was the planned research where you are looking into simplifying models to do a task, a very specific task, then with using less resources. I would say, I guess with a regular model that's just impossible. So I guess this has to be trained in a certain way that you can easily remove some of its whatever layers.
That's kind of the beauty. The paper is called "Keep What You Need," which is like it comes from a long line of papers with sexy titles in machine learning, and basically we take foundation models. So it's like really CLAP, wave-to-vec, stuff that wasn't specifically trained for the purpose of being trimmed, and we show that we can trim sometimes up to 80% of the network, but on a downstream task. And basically that's the thing. For instance, we take something like CLAP that was able to, classify all these things, and now we specialize it to speech, non-speech detection. So it's just separating speech from non-speech. But before that, it was able to say, it's a dog, it's music, it's a car, it's blah, blah, blah. We kind of make it dumber in the question we asked, so that's why we are able to remove quite a lot. But before that, I was working on this amazing thing called the lottery ticket hypothesis, which I'm a big fan of. And basically the idea was, this graph is not good. It looks more like that, which is basically you take a network, and once it's trained, it was shown in the original paper that you can remove around almost 99% sometime of the network and still have the same accuracy. If you remove 90% of the network, you actually outperform the big network with the smaller network. And of course, the big problem is that this works well for like simple problems, and as soon as you go into more complicated problems, then it's harder to go to these kind of high numbers. I actually applied it to generative models. It was like 5 years ago, I think. Yeah, 5 years ago. And I have this amazing graph, which, not really amazing, but anyway, which is basically that you don't have a big error multiplier, but I realized, like, I did this paper, I didn't sleep for 2 months, like trying to get these results. They were amazing. I was like, wow, I changed the game. And basically, after publishing, I thought, oh, but what does it sound like? I forgot to listen to the output, and it was awful. But the error multiplier is under 1.5. So yeah, be careful when you do. That's the problem with like sticking to numbers. So I agree, the problem with all these models is that we push numbers and we don't really know what they mean sometimes. Like saying, I can remove, I don't remember how much, 95% of the weights, and I only multiply the error by 1.2, which is not that much as a number you write. But when I listened to the audio, it was like really bad, like a lot of artifacts. So that's why my PhD student made this one, which actually this one works really well, but it's at more reasonable scales. I think he managed to remove 70% of the network, which is already quite a cool feat.
So when you, because I was also interested in this, no really deep understanding, but when you remove from a latent space, you mentioned something like we look at when the model responds to some input, and we keep that and we remove the rest.
Yep, that's kind of, so it's a simplified way to explain this graph, but it's not from a latent space. So basically here, like the latent space we actually don't touch. Let's say this is the latent space. This is the original paper we published. And in this paper, like this is classification. So it's a typical put audio and you get like this is music or a dog or blah, blah, blah. Actually what we do is we inject masks between the layers. So we have like every transform layers, right? And in the middle, we start by just injecting these modules, which is only one. So we multiply the output by 1. And then we basically train the mask. This doesn't change. We don't touch this thing. We just ask to like put the masks towards 0 and have a sparsity constraint. So we kind of gradually removing the thing to go to a point where we can safely, we know it's still doing well on the task, but this went down to 0. And at that point, we can remove the computation unit. So it's not really, if we were to do something as drastic as removing parts of the latent space, I think it would just crash down, because like it's, you can't remove things out of nowhere. So we just gradually learn what we can like shut down kind of slowly.
Something less technical. How would you say that the approach with Wavetable comes close to a new form of sound synthesis, like a technique?
Yeah,
how
actually,
do you
yeah.
consider that from your perspective?
Thank you for this amazing question. Like, in my opinion, it's the first step towards something that could be actually a new form of synthesis, because we enter a realm where we are seeing generators that have this constructive way of being used. Instead of having this thing that has an input and an output, and a button and that's it, the idea would be to constructively, that's what I'm missing, about machine learning. Let me show you my amazing slide, which I didn't have the time to show. I wish, in the end, this thing is going to look more like that, okay? Basically, most neural networks right now, they are like this big box. It's not about being a black box or whatever, I don't care. They are big boxes. They have X and they have Y, and then you have like all in between is just going on. And basically, like, if we could split into like smaller operations that could be modularized, then we would get, I think Wavetable is the first step to this idea of I can use signal in between the operations and I can perform on that operations that I guess in fine hopefully will lead to a new form of synthesis in itself. And what I'm missing right now is just the fact that this changes depending on the decoder. I think that's the kind of what I was showing, when I put the tables from electricity into like the model for voice. There is no kind of platonic hypothesis of representation between those different tables. And for me, if we manage to go to this point, then yes, we have a completely new way of working with sound. I hope. Maybe. Thank you.
Concerning this, so can't you just take any activities at any network level and compare it between one network that has been trained on that and another network that has the same architecture that is trained on something different, and then do what you're doing with the Wavetable? You interpolate between these activities.
Yeah, so basically that's the problem of mode connectivity. And mode connectivity is this idea that if you train the same architecture on two problems, or the same architecture on the same problem with different starting points, what is the interpolation possible between different networks? And actually it kind of doesn't work, even with simple problem. Interpolating between networks doesn't work because of the starting point, but you can show that if you find a nonlinear transform between one network to the other, you have this kind of valleys and basins of mode connectivity. So it's this idea that there exists a subspace of your parameter space, which if you project your transform on this subspace, then you can go on a direct path from one model to the next. And I completely agree. I would love for this to work, but like this, for instance, was done with like NIST training on, I think, ResNets. So it's kind of a simple, small model, and it's already, this is what you get basically, but if you learn a second model to go from one model to the next, they show there is some conditions when you have this kind of connectivity. So I guess, yes, I want to say you are completely right, it exists. The problem is it's not a given. It's not a property that you have just like that. But hopefully, one day, maybe.
All right, no further questions. So thank you so much again.